of the parent function for tangent of x. So if you remember, when you graph tangent of x, what makes tangent of x a lot different is the fact that, remember, you had those lovely vertical asymptotes to contend with. So remember, when we graphed the parent function tangent of x, when we looked at the parent function back in Unit 3, remember, we graphed only one cycle. And the parent function we graphed, it went from negative pi over 2 to positive pi over 2. And then you had your other key points at negative pi over 4, negative 1. You had your point at 0, 0. And then at positive pi over 4, you had your other key point at 1. So again, your parent function for tangent of x looks something like this. Again, you could graph more than one cycle. We could go from negative 3 pi over 2 to negative pi over 2. Remember, when we started a cycle for tangent, you started and ended with the vertical asymptotes. So that's what 2 cycles of tangent of x would look like. So we know they're functions. It passes the vertical line test. However, does it pass your horizontal line test? No. So it fails the horizontal line test because notice the horizontal line is intersecting the graph at more than one point. So just like we saw with inverse sine and inverse cosine, we have to restrict the domain to force tangent of x to be a one-to-one function. So the domain restriction we place on tangent of x is going to go from negative pi over 2 to pi over 2. So again, with a restricted domain, tangent of x from negative pi over 2 to pi over 2. Now, not only is it a function, it is a one-to-one function. All right? So when we studied the graph of tangent of x had a domain of all real numbers except odd multiples of pi over 2. And when I say odd multiples of pi over 2, you're looking at pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. So that's the domain of tangent of x. The range, and you can see that from the graph, is all real numbers. So the good domain restriction we'll place on tangent to force it to be a one-to-one is going to be from negative pi over 2 to positive pi over 2. So that's what's going to force tangent to be a one-to-one function. So remember what happens when you studied functions and their inverses with domain and range. What happens with the domain and range of a function and an inverse? They do what? They're going to switch. So the domain for your inverse tangent is going to be the same as the range for tangent of x. So the domain for inverse tangent is going to be all real numbers. The range is the same as the restricted domain. So that's going to go from negative pi over 2 to positive pi over 2. And just like somebody brought up a few minutes ago, the notation we see for inverses has this negative 1 exponent. That's how you can recognize you're dealing with the inverse. Or you may also see this arctan. It's just a different notation. It means inverse. So when you take a look at the graph of your inverse tangent, as you mentioned, the x's and y's flip-flop. So we know on tangent of x you have vertical asymptotes. On the graph of the inverse, instead of having vertical asymptotes, what kind of asymptotes are we going to have? Horizontal. So I'm going to have a horizontal asymptote at negative pi over 2 and positive pi over 2. Again, remember, we had those key points on the graph of tangent of x. Negative pi over 4, negative 1. So then on the inverse, it's going to go to negative 1, negative pi over 4 as one of my key points. I also have the point 0, 0. Again, when I switch x and y, it's still going to be at 0, 0. I have this other key point at pi over 4, 1. So on the inverse, it'll go to 1 pi over 4. So this is what the graph of your inverse tangent is going to look like. It looks a lot like that cube root of x function. Just like tangent of x, remember, looks a lot like that x to the third from algebra. Your inverse tangent looks a lot like that inverse of x to the third, that cube root of x function. So that's what the graph of the inverse tangent looks like. The only reason, ladies and gentlemen, I bring up this composition rule is because depending upon how your Algebra 2 teachers taught this to you last year, some of your Algebra teachers may have said, anytime you do a composition of a function and its inverse, it's always going to cancel out to equal x. Sound familiar? It's not the case for trig and inverse functions. If you followed my advice in the videos, and when you're doing composition of trig functions, if you always work the functions inside out, then you don't really have to worry about this theorem. But that's the only reason I'm really bringing it up, is because some Algebra 2 teachers may have said this is always true. It's not always true. So that's what we're going to talk about when we come back from lunch. All right, I'll see you guys after lunch.